You just saved a file. Your USB is now full. And here's the question nobody warned you about. Did it just get heavier? Not metaphorically, literally, physically heavier. The answer will completely change how you think about reality, and it has nothing to do with what you learned in school. I'm FactSpark, and if this kind of thing breaks your brain in a good way, hit subscribe because we do this every week. Let's start with something most people get completely wrong about how a USB actually works. When you save a file, you're not cramming tiny letters or compressed photos into a little box. There's nothing folded up inside. What's actually happening is something far stranger, and honestly, way cooler. Inside every USB drive, there's a memory chip. That chip is packed with millions, sometimes billions, of transistors so small they make bacteria look enormous. And each one of those transistors does one job. It acts like a switch. Either it's on or it's off. In the language of computers, that's a 1 or a 0. And here's the wild part. With nothing but ones and zeros combined in massive quantities, you can represent literally anything. A photo of your dog, a full movie, an entire operating system. All of it is just patterns of ones and zeros at an insane scale. Now, how do those transistors actually switch? This is where things get interesting. These aren't light switches you flip with your finger. They work using electrons. Each transistor contains a special region called a floating gate, and it's called floating because it's electrically isolated, suspended inside the material. This floating gate can trap electrons and hold them there, not for a few seconds, not for a few hours, for years, even when the USB is completely unplugged and sitting in a drawer.
That's why your files don't disappear when you turn off your computer. When you save something to a USB, what you're actually doing is forcing electrons into those floating gates using relatively high voltage pulses, tiny fractions of a second each. If the gate has electrons trapped inside, the transistor behaves one way. If it doesn't, it behaves differently. That difference is what the system reads as a 0 or a 1. It measures how each transistor responds to a small voltage. The response, whether current flows or gets blocked, gets translated back into ones and zeros, which become images, text, or sound on your screen. All of this happens at a scale so small it completely defies human intuition. The electrons aren't lined up like marbles in a jar. They're confined by electric fields, quantum tunneling, and energy barriers, engineered to keep information stable for decades. So, here's where the original question actually starts to bite. When you save data to a USB, you're changing the distribution of electrons inside it. You're forcing some of them to stay in places they weren't before. And to do that, you need energy. So let me ask you something, and I genuinely want to know what you think. Before we get into the physics of what that energy actually does to the weight of a USB, do you think the information itself has any kind of physical reality, or is it just an abstraction? Drop that in the comments. We'll come back to it. Because the answer to that question is more complicated than almost anyone expects. Now, here's where we have to reframe the question entirely. And if you ask it that way, the answer is, in principle, yes. But the effect is so absurdly small, it borders on philosophical. Here's the first trap. An electron does have mass, about 9.1 times 10 to the minus 31 kilograms. So, in theory, if you add electrons somewhere, you add mass. But here's the thing. When you write data to a USB, you're not creating new electrons from nothing. The electrons already exist inside the circuit. You're just moving them, repositioning them. Some end up trapped in floating gates where they weren't before, but the total number of electrons in the system doesn't change. So if the number of electrons stays the same, why would it weigh more at all? The answer isn't about electrons as particles. It's about energy. And this is where the story takes a sharp turn into territory that most people, even people who think they understand physics, haven't really sat with. Since the early 20th century, we've known that mass and energy are not separate things. Einstein's equation, E equals mc squared, tells us that any system that gains energy also gains mass. Not weight in the everyday sense. Mass in the relativistic sense. More internal energy means more total mass.
even if that increase is completely undetectable by anything you'd find in a kitchen or a lab. When you write data to a USB, you're doing work. You're using electrical energy to change the state of transistors. Some of that energy gets released as heat, but some of it stays locked inside the system, stored in what physicists call metastable electronic states. Which sounds intimidating, so let's break it down. A metastable state is a state that isn't the lowest possible energy state, but it can stay that way for a very long time without changing on its own. It's not the most stable thing possible, but it's not fragile either. Think of it like a ball sitting in a shallow valley on a hilly landscape.
The deepest valley would be the truly stable position. But if your ball is sitting in a smaller valley, separated from the deep one by a hill, it'll stay there. It's not going anywhere without a push. That's exactly what happens to electrons in flash memory. When an electron gets trapped in a floating gate, it's not in its lowest possible energy state. It could escape, but only if it had enough energy to climb over a very high energy barrier. Since it doesn't, it stays. For years, decades sometimes. That's why the data persists. The electron is in a metastable state. Stable in practice, but not absolute. And here's the crucial link. Keeping an electron in that elevated state costs energy. That energy is stored in the system, like a compressed spring or a rock balanced on a high ledge. And according to relativistic physics, any stored energy, chemical, elastic, thermal, electronic, contributes to the total mass of the system. So when we say a full USB is in principle slightly heavier than an empty one, it's not because files have weight. It's because the device contains more trapped internal energy stored in those metastable states. Now for the cold water moment. Let's say you have a USB with several gigabytes, completely empty, then completely full. How much extra energy is actually stored in the full version? Being generous, we're talking about energies in the range of picojoules or femtojoules per bit. That's unimaginably small. Even when you multiply that by billions of bits, the total energy is still ridiculously tiny. And when you convert that energy into equivalent mass using E equals mc squared, you get something in the range of 10 to the minus 21 or 10 to the minus 22 kilograms. To put that in perspective, that's far less than the mass of a single bacterium, far less than a virus, less than a microscopic speck of dust. No conventional scale would detect it. Most highly sensitive laboratory instruments wouldn't either. But, and this matters, the fact that it can't be measured doesn't mean it doesn't exist. In physics, some of the most important things are invisible at human scales. Now, here's a question that takes this even further. If information carries energy, and energy has mass, does that mean information itself has mass? Walk carefully here. Information as an abstract concept? No, it has no mass. The number 7 doesn't weigh anything. A written recipe has no mass on its own. The meaning of a sentence doesn't take up space. But any physical information, any information that actually exists in the real world, needs a physical state to represent it. And that physical state has energy. This idea was formalized in the second half of the 20th century through something called the Landauer principle. The physicist Rolf Landauer demonstrated that erasing information has an unavoidable minimum energy cost. No matter how efficient your technology, deleting a single bit requires dissipating at least a certain amount of energy as heat. It's a hard floor set by thermodynamics itself. This means information isn't floating somewhere outside the physical universe. It's anchored to material states, and those states obey the laws of thermodynamics and relativity. Someone might ask, if I move data from one USB to another, am I transferring mass? In a sense, yes. You're transferring energy associated with physical states, but the magnitude is so small that for any practical purpose, it's functionally zero. Now, you might be thinking, okay, but mass isn't the same as weight. You're right. Weight depends on gravitational field. A USB weighs one amount on Earth, less on the Moon, nearly nothing in open space. But its mass is the same in all those places. When people casually ask, does it weigh more? They're really asking about mass. And yes, in principle, a full USB has slightly more. If you had a perfectly ideal scale, No thermal noise, no air currents, no vibrations. The full USB would register slightly higher, not because it contains files, but because it contains slightly more internal energy. Now, what happens when you delete that information? Most people think deleting a file is like throwing something in the trash. It was there, now it's gone. Clean. But that's not what actually happens. When you click delete on most operating systems, the data isn't immediately destroyed. What happens is the system marks that space as available. The house is still there, the furniture is still there, the electrons representing your data are still exactly where they were. The electrical states are unchanged. That's why data recovery software can retrieve files that were deleted, because physically nothing was erased. If no new data has been written over that space, everything is still there. But now think about actual physical erasure, when the system genuinely resets a transistor, forcing trapped electrons out of the floating gate and back to their baseline state. To do that, you have to apply energy. The system has to push an electron over that energy barrier it was sitting behind. And once the electron drops back to its normal state, the energy that was maintaining that special configuration has to go somewhere. It doesn't vanish. It becomes heat.
That small excess energy dissipates through the chip material and radiates into the surrounding environment. Tiny, yes, but real. And according to relativity, when a system loses energy, it loses a corresponding amount of mass. So, stated as literally as possible, when information is physically erased, the device becomes very slightly less massive. Not because the data had volt, but because it's no longer maintaining those elevated energy states. The effect is unmeasurable, but conceptually, it's huge. Erasing information is not an abstract act. It's an irreversible physical process that leaves an energetic mark on the real world. The universe, even when you're deleting a grocery list, collects its toll. Now, let's take one step further, because a USB is a device where information has physical effects that are technically real, but completely negligible in practice. What if there were a system where information contributed to mass in a way that actually mattered? There is, and it's about as extreme as physics gets. Black holes. A black hole isn't just something very heavy. It's an object where gravity is so intense that not even light can escape. You know that already. For a long time, physicists assumed black holes were extremely simple objects. From the outside, only three things seem to matter: how much mass they have, whether they're electrically charged, and how fast they spin. That's it. Everything that fell in seemed to disappear without a trace. But that picture started falling apart when physicists realized something unexpected. Black holes obey the laws of thermodynamics, and one of those laws involves entropy, which you can think of simply as a measure of disorder, or more precisely, the number of possible internal configurations a system can have. In normal objects, like a gas or a star, entropy grows with volume. More space means more ways to arrange particles. So what happens with black holes is deeply strange. Their entropy doesn't depend on the volume of what's inside. It depends on the area of a very specific surface, the event horizon, the boundary beyond which nothing can escape. This suggests that all the information inside a black hole, everything that has ever fallen in, isn't distributed throughout the interior the way you'd expect. It's somehow encoded on that surface. The larger the event horizon, the more information the black hole can store. The entropy of a black hole becomes a direct measure of its information capacity. That's not a metaphor. That's a physical property. In these extreme objects, information stops being abstract. It becomes part of the structure of space and time itself. You literally cannot fully describe a black hole without accounting for the information associated with it. Its mass isn't just compressed matter. It's mass, energy, entropy, and information all tangled together in a way that's fundamental to how the universe works at its most extreme. Let's bring it back down to something more familiar. Imagine you send an email. Not a big one, no attachments, just a few lines of text. From an everyday perspective, you're obviously not sending mass. Your room doesn't get lighter when you hit send. But from a relativistic perspective, you are sending mass.
because you're sending energy. That email travels as electromagnetic signals, electrical pulses in fiber optic cables, radio waves between antennas, photons bouncing between servers. And all of that energy has an equivalent mass according to E equals mc squared. The problem is scale.
A typical email might require energy on the order of a few microjoules to transmit across a network. Convert that to equivalent mass, and you get a number so small it doesn't even make sense to write out all the zeros. We're back to talking about less than the mass of a single molecule of water. Now, multiply that by millions of emails, billions. Even if you sum up all the internet traffic on the entire planet for an entire day, the total mass associated with that energy is still negligible compared to any everyday object. It wouldn't come close to the mass of a single grain of sand. For the internet to have any appreciable mass, you'd need to concentrate an absurd quantity of energy in the form of information all at once. Something that's completely beyond what technology or the planet itself could handle without catastrophic consequences. So why hasn't anyone directly measured this mass difference? Because we don't have scales anywhere near sensitive enough. Trying to measure a mass difference on the order of 10 to the minus 21 kilograms in a macroscopic object is currently impossible. Thermal noise, air molecules landing on the surface, humidity changes, ambient radiation, all of these create fluctuations many orders of magnitude larger than the signal you're looking for. Here's how small we're talking. A single water molecule attaching itself to the surface of a USB has more mass than all the information stored inside it. One molecule, not a drop, not a speck, a single H2O molecule. So let's land on the final question, the one that ties everything together. Is information real, or is it just an abstraction? Information as a concept, a number, a word, a theory, a story, is abstract. The number 8 doesn't have mass.
A poem doesn't take up physical space. The meaning of a sentence isn't made of anything. But modern physics forces us to add a critical condition. Every piece of information that actually exists in the universe must be represented by some physical state. There is no information floating freely, independent of matter or energy. It always needs a substrate. Atoms arranged on paper, electrical charges in a chip, magnetic fields on a hard drive, electrochemical signals in your brain. And that substrate is never neutral. It obeys very specific physical laws. To store information, you spend energy. To change it, you spend more. To erase it, heat is inevitably released. No matter how perfect the technology, that cost cannot be avoided. It's built into the structure of thermodynamics at the most fundamental level. So while information may be abstract in its meaning, it is profoundly physical in its implementation. It has measurable consequences. It consumes energy. It increases entropy. And in a strict sense, it contributes to the mass of every system that contains it. Information isn't just a tool we use to describe the world. It's something the universe itself has to hold up. And that's where we'll leave it. If your brain is still intact after all of that, good. If not, that's the price of thinking clearly about reality. Go back to that question I asked earlier, whether you think information is real or just an abstraction, and drop your answer in the comments. I'm genuinely curious how people land on this after seeing the physics. Thanks for watching, and I'll see you in the next one.